Today we're going to talk about this book on this surface right here. So when the physics book rests on the flat surface, the force diagram, or the forces acting on the book, are simply the weight going down and the normal force pushing upwards. The book has no desire to go anyplace. Inertia says that it wants to stay at rest. So since it has no desire to go anyplace, then there's nothing that's opposing its motion, because there is none, or its desire for motion, because there's none of that either. But the second I push on this book in that direction, now the book desires to move in that direction. So something is opposing that desire. Specifically, something has the same magnitude acting in the opposite direction, because the book is still at rest. It's not accelerating. So when I push in this direction with some force F, that gives rise to a static friction force acting in the opposite direction. And as long as this box is still in equilibrium, as long as it's still at rest, then the size of those two vertical forces have to be equal to, or horizontal forces have to be equal to each other, in addition to the two vertical forces having to be equal to each other. We've talked about that. And just recently we talked about, hey, instead of me pushing this thing straight across, what if I push down and across? So you can see my arm at an angle. So now what happens if I push down and across? Well, if I push down and across, then that picture turns into this picture. But we have an issue with this particular picture, because we can't work with this force and we can't work with that force because it's not either in the X plane or in the Y plane. And up until this stage, we've been saying that the only forces that we can work with are ones that are in the X plane or in the Y plane. So the normal force is okay, that's in the Y plane. Weight is always going towards the center of the earth, that's in the Y plane. The force of friction is parallel to the surface. But in this particular case, we are applying a force downwards at an angle. We can't deal with that. So what have we been doing? Well, we've got to break that thing into its components. So we don't deal with that. Instead, we deal with this force picture. This force picture's got that force right here broken into its components. Part of that force is pushing across, and part of that force is pushing downwards. Now we can work with this because the forces are all either in the X or in the Y. And now we can work with it. And that's what we've been doing the past couple days. Now keep that in mind. We're just going to change the lingo up a little bit. Instead of saying we can only work with forces in the X or in the Y, instead we're going to say that we can only work with forces that are either parallel to the surface or perpendicular to the surface. That's essentially what we've been doing, but we've been using X and Y. But we can't do that anymore, because guess what we're going to do now? We are now going to tilt the surface and talk about what happens when we tilt this surface. So let's think about the forces that are acting on this textbook. Well, the one force that is, ever present is the idea of the force of gravity, or the weight of the object. Now, certainly, like the only things that dictate the weight of the object are the mass of the Earth, the mass of this object, and how far from the center of the Earth this object is. Certainly, us just tilting this board doesn't change any of that. So the weight of the object is always directed straight down towards the center of the Earth. This stays exactly the same when I tilt that surface. So there's the weight force. Notice it's exactly the same. The weight of the book didn't change. It didn't change in size, and it didn't change in direction. The Earth governs all of that. What we do can't change the weight of that book. All right. Now, what it did change, though, was the normal force. And that's really our main point here today. And because the definition of the normal force is the force that acts perpendicularly up from a surface. We've slanted our surface now. So now if we've slanted our surface, then the normal force looks like that. It's perpendicular to the surface, but it no longer is opposite in direction to the weight. And everything we've done up until now always has that normal force opposite the direction of weight. But the definition of the normal force hasn't changed, the force that acts perpendicular to the surface. It's just so happened that our surface has always been flat, so therefore the weight would act perpendicularly down and the normal force would act perpendicularly up. But changing the angle of the surface doesn't change the weight, but it does change the normal force. Okay? Now, there's something else at play here, because as soon as I tilt this surface, the book has a desire to go down towards the bottom of the incline. Now, you can't necessarily see it because I've made it so that the book stays put, right? But if I take the baseball and I put the baseball on here, whoa, the baseball is going to want to go down the incline. That baseball will go down the incline. It's got a desire to go down the incline. The book has a desire to go down the incline. Well, friction opposes our desire for motion. The book has a desire to go down the incline, so the force of friction in this particular case, it's a static friction. The force of static friction pushes up on the textbook, or rather up the incline, because friction always goes parallel to a surface. Now, we had a problem here, right? We had a problem with this picture because this force right here, F, was not either parallel or perpendicular to the surface. Well, guess what? We've got a problem over here. We don't have a problem with the friction force because it's parallel to the surface. We don't have a problem with the normal force because by definition, the normal force is perpendicular to the surface. And it's okay to have forces that are either parallel or perpendicular to the surface. But the weight goes directly down to the center of the earth. And in this particular case, that weight is no longer either parallel or perpendicular to the surface. So what did we do to this? We took that force and we broke it into components. Why? Because this force wasn't parallel or perpendicular to the surface. So if weight isn't parallel or perpendicular to the surface, then we've got to break weight into its components. So we're going to do the same thing that we did here, except we're going to do it with weight. So now, if I've got this incline, I can keep the friction force because it's parallel to the surface going up the incline. I can keep the normal force because it's perpendicular to the surface going up the incline, but I've got to break the weight into components. Now, what components did I break that force into? One force that's parallel to the surface and one force that's perpendicular to the surface. Well, I'm going to do the same thing. Here, this is now, I call it W parallel, and I call this W perpendicular. If I would have asked you what force takes this ball and brings it down the incline, everybody would have said gravity, right? Everybody would have said the weight of the object, but the weight of the object goes down. Technically, it is W parallel's job to push things down the incline. So the job of W parallel is to push objects down the incline. The job of W perpendicular is to push objects onto the incline. So W perpendicular forces objects onto the incline because the incline is trying to push them up. W parallel pushes the objects down the incline. And those are the two jobs for those two forces. And guess what? Now we've got all these things, and all of our forces are either parallel or perpendicular to the incline. So we now work, instead of some of the forces in the X and some of the forces in the Y, now we work with some of the forces perpendicular to the incline and some of the forces parallel to the incline. So we know that this book is in equilibrium. So we know that the sum of the forces acting on the book is 0. Well, we've really got two paths to go here. the sum of the forces perpendicular to the incline equals 0, and the sum of the forces parallel to the incline equals 0. Well, what two forces are parallel to the incline? FF minus W parallel equals 0. So from a size perspective right now, since we're in equilibrium and these are the only two forces acting on the object, then FF equals W parallel. Well, over here, we've got the normal force and weight perpendicular. So Fn minus W perpendicular equals 0, and therefore Fn is equal to W perpendicular. So we can't get caught up with always saying the normal force is equal to the weight. And we've done a nice job of that when we've either pushed directly down on an object or us pushing at an angle to the book or the object, right? Now, we've got another situation, but it rings true, right? We have to adjust to the situation. Now, there's components of the weight that are either parallel or perpendicular to the incline. And in this particular case, the weight and the normal force are equal in magnitude to each other. All right, now, logically, right, what happens here? If I take this marker or a different marker, all right, and if I put it this way, the marker, if I have an object that were slipperier, oh, maybe this thing will work, right? So if I take this thing and I put it on the incline, still not going to work. I got to get something super slippery. I don't know if I even have anything slippery enough. Oh, there we go. All right. So if I take this bottle of what you call it, if I take this bottle of lotion and I put it on the incline here, this bottle goes down the incline. It accelerates down the incline. Well, what happens if it accelerates down the incline? Well, because it's a slipperier surface, this friction force is smaller than the parallel component of its weight. Right now, for this textbook, the parallel component of the weight is equal to the friction force. But if they become out of balance, then we're going to accelerate down the incline. Now, sometimes we get forces that push up the incline. Sometimes we get other forces that push down the incline, right? So in other words, right now, how can I put this thing out of equilibrium? If I go this way, then I'm adding an extra force down this way. So my force plus W parallel was bigger than this, and therefore our forces wouldn't sum to 0 anymore, they'd sum to MA. We should now be used to the fact that we can change each situation based on what happens. But what we're not used to is mathematically breaking up this weight into its components. So let's go through that here. So if I draw this incline and I draw this thing and I solely focus on our components of weight. So I'm going to draw them a little bit different. I'm going to draw them so that they form our component triangle or our right triangle. All right, so I'm going to get this thing, let's put it down here a little bit because I'm going to have to make my incline a little bit bigger. All right, so now W perpendicular goes like that, right? It's perpendicular to the incline. W parallel, I can complete my triangle like that. It's parallel to the incline. So there's my triangle right like that with respect to the incline. Now let's think about this, okay? Now, my incline is lying on the ground, and it's inclined at some angle theta. Now, you're not going to have to duplicate this, but I think it's worth doing. It's worth showing when we talk about this. Okay? So look at right now, this angle right here is 90 degrees. How do we know it's 90 degrees? Because this is the perpendicular component to the incline, which means that vector has to be perpendicular to the incline. This is 90 degrees as well, because the ground and the weight make a 90-degree angle, right? The weight goes straight down so that it's perpendicular to the ground. So that's 90 degrees. Well, I got a bunch of triangles here. One of my triangles is this thing. And if this triangle has a 90-degree angle and theta, then the last part of that triangle is 90 minus theta. Now, from geometry, we know that a straight line has 180 degrees. Well, look at my straight line right here. It's got 3 angles. It's got a 90-degree angle. It's got an angle that is 90 minus theta. And it's got some angle right here that's really at the crux of my trig triangle. So there's W perpendicular, there's W parallel, and there's my weight, W. This question mark is that thing right there. Now, when I redrew this triangle, it might be twisted a little bit, but this question mark is that question mark right there. All of this has to equal 180. So 90 plus 90 minus theta, plus theta rather, plus question mark must equal 180 degrees. Oh, my bad, this is a minus. 90 plus 90 minus theta plus question mark must equal 180 degrees. Well, guess what? The only way to get all this to add up to 180 degrees is question mark must equal theta. So all that's telling us is this. The angle that the incline makes with the ground is the same as the angle that's right in here on my trig triangle. So now what does that mean? Weight is my hypotenuse, this is my adjacent side, and this is my opposite, and this is my opposite side. So what that means is that W perpendicular, since it's the adjacent side of this trig triangle, is associated with the cosine of theta. So the portion of the weight that's holding the object on the incline is equal to the weight times the cosine of the angle. And the portion of the weight that's parallel to the incline is equal to the weight times the sine of theta. And we don't have to memorize much in this class, but you got two options here. You can either understand how to duplicate this proof, which is doable, or you could just figure out and understand or memorize that the W sine theta is equal to our parallel component and W cosine theta is equal to the perpendicular component. Now, there's all sorts, just like anything, there's all sorts of different things that we can do with this information. All right, and we will continue to build on that in the rest of today's lesson and building into tomorrow. And then in addition, like there's just some stuff that you've got to figure out on your own when presented to this with this situation, since we've given you the basics of the situation.